4.1, we're going to talk about the derivative and the tangent line problem. So there's 4 major topics in calculus. We've got these 4. The first one is the tangent line problem. But all 4 of these involve limit notation. So limits do not go away. We keep using limits to help us solve different things. So we're going to use tangent lines to help us find the slope of a graph when it's non-linear. So a tangent line touches at one point. So we could find the slope of the line tangent to our circle here at the given point. So we've got 3 different examples here. To find the rate at which the graph rises or the graph falls at a single point, we can find the slope of the graph at that point, which is just the slope of our tangent line. So depending on what point you pick on your graph, your slope could be different. So looking at the example on the left, if we had the point P here, what's the slope of our line when it's horizontal? What's the slope? 0. Our slope would be 0. But if I picked a point on my graph here and my tangent line went like this, would our slope be 0 of the red line? No, it would be some negative slope because our line would be decreasing. So it just depends on what your point is that you pick. Before we get into like tangent line, it talks about the secant line a little bit. So we could find the slope of a line given 2 points on our line. We use our slope formula, y2 minus y1 over x2 minus x1. So if we have a secant line, meaning that it touches in 2 points, we can find our slope using the slope formula. But instead of using y1, y2, x1, x2, it uses the point C and f of c, and then c plus whatever our change in c is, and then f of c plus our change in c. So we can find our slope of the secant line given 2 points when we use the slope formula and we use our c and dx. It simplifies to our difference quotient. So the difference quotient we use a lot in this section. So the next page talks about the secant line. So if we had 2 points and we found the slope through those 2 points, the closer that our second point gets to that c and f of c, the more exact our slope of the line is going to be, which is why we use the tangent line where it touches in 1 point. So we don't really talk about the secant line, it's more just the tangent line. But given the tangent line, we'll find everything that we need. We'll find the slope of the tangent line. So it's just a more exact slope. So our slope of the tangent line comes from the limit of our difference quotient. So the limit as dx approaches 0 of f of c plus dx minus f of c over dx. This is our slope of the tangent line, where c is going to be a point on our graph that's going to be given. So x equals c. It may give you a point, whatever your x value is in that point, that's going to be your c. So we're going to plug that in to help us solve. So let's look at example 1. It says find the slope of the graph of f of x equals 2x minus 3 at the point 2, 1. So we're going to use the limit with the difference quotient to help us find the slope here. So we have the limit as dx approaches 0 of f of c plus dx minus f of c over dx. So let's plug in f of c plus dx. I'm going to take c plus dx and plug it into the x in my function here. So this would be 2 times c plus dx minus 3 minus, for f of c, I'm going to take c and plug it into the x in my function. So that would be minus, I'm going to put it in parentheses since we've got a couple terms here, 2 times c minus 3 over dx. So let's simplify. You can simplify here using c's, or we can plug in our value for c. So remember, x equals c. So what would our c value be? What's our x here? 2. 2 would be our c. So you can plug that into the c's to help you solve. Or we can simplify using c's and then plug it in at the end if we need to. So I'm going to simplify using the c's here first. So let's distribute the 2. We get 2c plus 2 dx minus 3. I'm going to distribute the negative here. So minus 2c plus 3 over dx. 2c's cancel. 2c minus 2c. And negative 3 plus 3 will cancel. So we're left with 2 dx over dx. Which simplifies to what? 2. So the limit as dx approaches 0 of 2 would equal what? 2. And this would be our slope. Yes. From the beginning, we knew what our slope was going to be because when you have a linear function, your slope doesn't change no matter what point you pick on your graph. We knew that our slope was going to be 2. When it's just a linear function, that's what your slope is. But if we had like a parabola quadratic function, depending on what point we had on our quadratic function, your slope's going to change. So it says the graph of a linear function has the same slope at any point, like we did in the last one. This is not true for non-linear functions. So it's not always going to be just the slope of the function. Another point that this slide makes is that if we take the limit of our function or of our difference quotient of the function, we get infinity or negative infinity, then we have a vertical tangent line. So it says the definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. For vertical tangent lines, you can use the following definition. So if our limit goes to infinity or negative infinity, our tangent line would be vertical. What's the slope of a vertical line? Undefined. Perfect. If we picked a point on our graph here and our tangent line was vertical, when we take the limit of whatever our function is, our limit would go to infinity. So if our limit goes to infinity or negative infinity, we know that we have a vertical tangent line. The next topic we have is the derivative of a function. So derivative of a function also means differentiation. So it's two of the same thing. You can say derivative. Differentiation is a different tense of the word. Which we use the same formula. So the derivative of f at x would be the limit as dx approaches 0 of fx plus dx minus f of x over dx. It's the same formula, but the c turns into x's here. So when you find the limit, you'll have x's in your answer. It's not just going to be a number because we're not finding the slope. So this new function gives the slope of the tangent line to the graph of f at the point x, comma, f of x, provided that the graph has a tangent line at this point. The process of finding the derivative of a function is called differentiation. A function is differentiable. So again, same thing. A function is differentiable at x if its derivative exists at x, and is differentiable on an open interval if it's differentiable at every point on the open interval. So So when we find the derivative, you want to make sure you name it. So this symbol is a symbol for derivative. It's read as f prime of x. We'll mostly see f prime of x or dy over dx, which is read as dy dx. So these are the two most common symbols we'll see for derivative. You may see the other ones, but not really in Calc Honors. If you took calculus in college, you might see the other ones more often, but they mean derivative. So using limit notation, we find the derivative using our difference quotient here. Just restates it for us. Let's look at example 2. So we want to find the derivative of x cubed plus 2x by the limit process. So as we go on into this chapter, we'll talk about other ways we can find the derivative, which once you see it'll be like a major shortcut. But for now, we're going to use the limit process. So the limit process is the limit as dx approaches 0 of f of x plus dx minus f of x over dx. So to find f of x plus dx, we're going to take x plus dx and plug it into our x's in our function. So we get x plus dx cubed plus 2 times x plus dx minus f of x, which is just our function. So I'm going to put it in parentheses, x cubed plus 2x over dx. We're still finding the limit of this. Let's simplify. So x plus dx cubed, you can write it 3 times and FOIL it all out if you want. Or we could use our Pascal's triangle shortcut if we remember. So Pascal's triangle, we start with a little triangle of ones. Then we add the 2 numbers above it. Each row is going to start and end with a 1. So 1, 2, 1. The next row would be 1, 3, 3, 1. Since it's a binomial to the 3rd power, we're going to stop here. But if it was to the 4th power, we'd have 1, 4, 6, 4, 1. But we're just dealing with the row with 3's. Because it is x plus dx to the 3rd power. So this is a little bit of a throwback, trying to remember what Pascal's triangle is. I would practice it in the homework doing it this way because it's going to be easier than writing it 3 times and foiling it all out. It's also less room for error. So practice it when you do the homework questions. If you want more questions to practice, I can make some up for you, but practice this way. So here I'm going to start with my constant 1, 3, 3, 1. Then I'm going to use my first term, so that's x. I'm going to start with x to the 3rd power, so whatever our degree is, x to the 3rd power. We're going to decrease from there. So then x squared, x to the 1st power, and x to the power of 0. Then I'm going to use my second term that I have, so that would be dx. We start from 0 and go up from there. So dx to the power of 0, dx to the power of 1, dx to the 2nd power, and dx to the 3rd power. I'm going to put it in parentheses so we don't get confused. So because it's a plus, all of our signs are going to be plus. Now we're just going to combine each column together. Dx to the power of 0 would just be 1, so that goes away. So we have 1 times x cubed would be x cubed. Plus 3 times x squared times dx would be 3x squared dx. Then 3 times x times dx squared would be 3x dx squared. Plus x to the power of 0 is just 1, it goes away. So this would just be dx cubed. So this is our Pascal's triangle shortcut. It's going to be a little bit easier than writing it out 3 times and foiling them all together. So this is just the first binomial cubed, this simplified. So we have x cubed plus 3x squared dx plus 3x dx squared plus dx cubed. Next, I want to distribute the 2. So plus 2x plus 2 dx. And then we're going to distribute the negative. So minus x cubed minus 2x over dx. All right, let's simplify. So if we did it right, everything that doesn't have a dx will cancel. So negative x cubed and positive x cubed cancel. 2x and negative 2x cancel. Since we have a dx on the bottom, we can divide out a dx from each term on top. So dx on the bottom is going to take away a dx here, just one of the dx's from here, one of them from the dx cubed, so we're left with 2 of them, and then the dx from the third one, or from the fourth. So we're left with 3x squared plus 3x dx plus dx squared plus 2. And we're still finding the limit of this. So we can plug in 0 into our dx's. We're going to use direct substitution from here. So 3x times 0 would just go away. This becomes 0. 0 squared would just be 0. So we're left with 3x squared plus 2. So this would be our derivative. Last step, make sure you name it. It'd stink to lose points after all of that work and you forget to name it. So it says, remember that the derivative of a function f is itself a function, which can be used to find the slope of the tangent line at the point x comma f of x. So if this question said, find the slope of the tangent line, we would do that same work, but it would give us a point. So it'd say like at the point 2 comma 0. We would take 2 and plug that into our x. So it's kind of the same idea what we were doing in the first part of the lesson where we had c, but if we worked it all out, instead of c, we have an x, we would just take the x value and plug it in. And that would give us the slope. So the last thing we're going to talk about in this section is differentiability and continuity. So we're going to talk about if something's differentiable, then it is continuous. So we have the same formula here to help us see if something's continuous or not. It's derived from the same thing, our derivative formula, which is our tangent line formula, same idea. If something is not continuous, then it's not differentiable. So here, our function is not continuous at x equals 0, so it's not differentiable at x equals 0. So you need something to be continuous in order for it to be differentiable, in order to find the derivative of it. So the function is not continuous at x equals c, it is not differentiable at x equals c. So differentiability and continuity go hand in hand. If it is differentiable, then it is continuous. However, the converse is not true. So if it's continuous, that doesn't mean that it's differentiable. Just because something is continuous does not mean it's differentiable. In example 3, here we have the absolute value of x minus 2. This is continuous. If I was a little ant, I could walk all the way along this graph and be fine. But it's not differentiable. Because we have a sharp turn. So if something has a sharp turn, it is not differentiable. Even though it's continuous, it's not differentiable. So there's some questions on the homework. There's some multiple choice questions on the homework like this, where it asks if it's differentiable. If you have a sharp turn at that x value, it would be not differentiable. So if we used our formula there, the limit as x approaches 2 from the negative direction, we would get what we've been doing, this little formula. We've seen this on the last quiz and test, where if we approach from the negative direction, we'd get -1. If we approach from the positive direction, we'd get +1. So since we get different values, since they are not equal, then we can't take the derivative. It would be not differentiable. Can't take the derivative here. So f is not differentiable at x equals 2, and the graph of f does not have a tangent line at the point 2, 0. Again, it says the same thing. If f is differentiable at x equals c, then f is continuous. So if it's differentiable, then we know that it is continuous. This just summarizes the last couple slides. So if a function is differentiable at x equals c, then it's continuous at x equals c. So differentiability implies continuity, but just because it's continuous does not mean that it's differentiable. And the example that we have is when we have a sharp turn. If your graph is a sharp turn, even though it's continuous, it is not differentiable at the sharp turn. So find the slopes of the tangent lines to the graph of f of x equals x squared plus 1 at 0, 1 and -1, 2. So we're going to use our limit to help us find the graph. So the limit as dx approaches 0. Here, since we have a value, it's asking for the slope. We're going to use the formula with c's. So instead of x's, we're just going to use c's. So f of c plus dx minus f of c over dx. If you want to, you can plug in your value for c right away. So here, what's our c? 0. The x value is a c, so c is 0. So we could plug in 0 into c. So I have 0 and 0. So this is just asking for f of dx. So I'm going to plug dx into my x's. So we have dx squared plus 1 minus f of 0. If I plugged 0 into my x's, what would we get? 1 over dx. And we're still finding the limit of this. The limit as dx approaches 0. So 1 minus 1 would cancel. We have dx squared over dx. What would this simplify to? Dx. We'd take away one of the dx's on top. So the limit as dx approaches 0 of dx would be what? 0. So that would be our slope. I'm going to do kind of a bonus part to this question. We'll do B also, but I'll say example 2. Is to find the equation of the tangent line. Find the equation of these tangent lines. So starting with A. So our first line was at the point 0, 1. And what was the slope that we found at this point? 0. how do we come up with an equation of a line given a point and the slope? Point-slope form. Perfect. So our point-slope form is y minus y1 is equal to m times x minus x1. So if I plug in everything I have y minus 1 equals 0 times x minus 0, which will just be y minus 1 equals 0. So what would y equal? 1. So that would be our equation of the tangent line. Now let's do B. Find the slopes of the tangent line to the graph through the point -1, 2. So we're going to do the same thing here. We'll find the limit as dx approaches 0 of f of c plus dx minus f of c over dx. What's our c value here? -1. Awesome. This is our c. So you can either plug it in now or plug it in at the end. Doesn't matter. I'll plug it in now. So I'm going to replace c with -1. So the limit of dx approaches 0 of f of -1 plus dx. So I'm going to take -1 plus dx and plug that into my x. So this would be -1 plus dx squared. What's a better way of writing -1 plus dx? A little bit cleaner, I would think. dx minus 1. I'm just going to write it a little bit nicer for us because it's going to be easier to work it out. So dx minus 1 minus, let's find f of -1. If I plug in -1, -1 squared plus 1 would be what? 1 plus 1 is 2. So minus 2. I forgot something, didn't I? Plus 1 here. I forgot the plus 1. Plus 1 minus 2 over dx. Because when I plug in -1 plus dx into the x, I can't forget that plus 1 there. All right. Let's simplify now. So dx minus 1 squared, if you want to, write it twice and FOIL it out. Or I know that it'll be dx squared minus 2 dx plus 1 minus 2 over dx. Anything cancel? 1 plus 1 would be 2, and 2 minus 2 is 0. Anything else? The dx, I can take away a dx from each term on top since they both have dx's in it. So I'm going to take away 1 from the dx squared and a dx here. So we're left with dx minus 2. So the limit as dx approaches 0 of dx minus 2 would be what? -2. So -2 is our slope. Right, let's do the second part of this question. So B was through the point -1, 2. So given a point, what was our slope? -2. Given a point and the slope, we can use our point slope form. Plug it in. So y minus y1 is 2 is equal to -2 times x minus -1, which will turn into plus 1. So y minus 2 equals -2x minus 2. If I add 2, we get y equals -2x. So that would be our equation of the tangent.